All right, guys, we are on to Unit 7 here now. Unit 7, we are talking about our chemical equilibrium, okay? So we've talked about last unit about thermal equilibrium, where we would maybe have two species, one at a cold temperature, one at a hot, and they can interact with each other where our atoms are bouncing off each other and are transferring kinetic energy. Now we are talking about our chemical equilibrium. And so what we have, right, if we think about our chemical reactions, right, we can have a forward reaction and a backwards reaction, right? So we've talked about how we'll have exothermic and endothermic reactions. An exothermic, right, it's going to release energy. Endothermic is going to absorb energy into the system. But what if our reactants and our products are really close in energy, right? Then there's really nothing to say why we can't go forward or back, okay? So we've talked about the forward reaction and the backwards reaction before when we talked about reaction rates, okay? So when we talked about right, a multi-step reaction rate, we had a fast equilibrium where we could have the forward reaction and the backwards reaction, okay? So this arrow here is our arrow that we use with equilibrium, okay? So within an equilibrium, rather than when we talked about rates, right, we have the forward reaction rate, which was K, maybe K1, and the backwards reaction rate constant was K minus 1. Well, with equilibrium, we actually use K as well. But this is why I said it's really important to denote lowercase k's versus uppercase k's, okay? But what's cool is that our forward reaction divided by the backwards reaction, right? This rate constant, right? The rate constant of our forward reaction, rate constant of our backwards reaction is really equal to our uppercase K, okay? This is our equilibrium constant, okay? So graphically, right, we can think about this if we have two different species, right? Maybe one starts we'll have our reactants and it's in equilibrium with our products, right? We are going to start with 100%. That would be our reactants. And down here at 0 would be our products. But at some point, right, we get this reaction. So at some point, we're going to get a flat line here where we're not going to see any more changes, okay? Right? We are going to have an equilibrium established where our forward reaction is occurring at the same rate as the backwards reaction, okay? So the forward reaction happens at the same rate as the backwards reaction. Okay? It is not that at a certain point we just stop getting any reaction at all. No, there are going to be reactions occurring. There is going to be the forward reaction. There is going to be that backwards reaction occurring as well. But we have the forward reaction and the backwards reaction occurring at the same rate, okay? And this is a really important key concept, okay? So what we'll have, right, this ratio between our products and reactants is really our equilibrium constant and the reaction quotient, okay? That's really the important piece there, okay? So whenever we have an equilibrium constant, right, we say that is K, that is dependent on the reaction conditions, but depending on the reaction conditions that we change, K may not change, okay? So we'll talk about ways that will change K or will not change K. The reaction quotient conversely, is really just the relationship at that point, okay? So the relationship between our products and reactants at whatever point we are, okay? So wherever we start at or wherever we're asking about, okay? So whenever we have our equilibrium constant, right, we can write our equilibrium constant and we use this form here, okay? So if we have this chemical reaction up above, you see, right, that chemical reaction, we have products C and D. Products C and D are on the top, and on the bottom are our reactants A and B, okay? And each of these is brought to the exponent, okay, of our coefficient, okay? So it's always going to be the concentration of our products divided by our reactants, okay? Always going to be the products over the reactants, and we always use the coefficients from our balanced chemical reaction for our equilibrium expression, okay? That is totally different from our rates before, okay? So remember from our rates before when we can use those coefficients, because it is different from our when we can use our coefficients with our equilibrium, okay? So, oops, it is different down here, okay? So it is really important, like I said, to differentiate our uppercase K and our lowercase k, okay? So with our equilibrium, we are going to use the uppercase K. All right, so let's get some practice here just writing the equilibrium constant, okay? The equilibrium expression. So if it asks us to write the equilibrium expression for a chemical reaction, right, we are always going to write K equals, and then it is going to be our products. Okay, so our products, well, concentration of NO2, we have a 2 in front, so that's going to be squared, divided by the concentration of N2O4. Okay, so that's relatively easy, but we notice that we've got our states labeled here, okay? So our gases, rather than using concentrations, which aren't very easily measured with our gases, instead what we're going to use are pressures, okay? So whenever we have a gas, we are not going to use concentrations. Instead, we're going to use pressures, okay? So pressure for NO2 squared over the pressure of N2O4. So we remember our partial pressures from before. Hopefully we do, because right, our partial pressures add up to the total pressure. Hopefully we remember that because they are coming back right now, okay? So whenever we have a gas, we are always going to use pressures rather than our concentrations, okay? When we have an aqueous mixture, right? We've got ions mixed in there in water. Then we are going to use our concentrations, okay? But we should be able to, like I said, write the K expression, okay? So the equilibrium expression, K equals pressure of NO2 squared divided by the pressure of N2O4, okay? So always going to be products over reactants, and we always use our coefficients as the exponents, okay? Now, let's look at writing the equilibrium expression for this reaction. That should be simple enough, right? We're going to write K again. K equals, well, products, okay, pressure of NO2 divided by pressure of N2O4, but now it's to the, 1/2 power. Now, if you look at this, that's easy enough, but if we look at this, we see, this reaction for part B is half the reaction of part A. I took and I cut each of our reactants and products the coefficients, and I cut those coefficients in half, right? So whenever you cut the coefficients in half, what's going to happen to k? Well, k is going to be to the 1/2 power. So our equilibrium expression, when we divide our reaction in half, the equilibrium constant is going to go to that power, okay? So we cut it in half, so k is to the 1/2 power, okay? This is going to be important if we start combining reactions, something kind of like our Hess's law problems from last unit. Again, we notice that Hess's law, right, we added our enthalpies, but now when we add reactions or when we cut reactions in half, right, we're changing them, right? We have different rules for our K expressions, okay, for our equilibrium expressions. So that is different again. We are going to talk more about it here, and we'll get all of our rules, okay? So now let's look at these two reactions, okay? So now we say, okay, write the equilibrium expression for this reaction. That's pretty easy. We're going to write K equals, well, products, that would be pressure of N2O4 divided by the pressure of NO2. That's going to be squared. Now if we compare A and C, right, I have flipped the reaction. So if you flip the reaction, now we have 1 over our K value, okay? So it is not just the negative K value. Instead, it is 1 over K, okay? Again, this is going to become important when we start adding our reactions, okay? So let's summarize here, right? When we cut the reaction in half, we get K to that power. When we flip the reaction, we get 1 over K. All right. Oh. So let's talk now about actually adding our reactions. Okay. So when we add our reactions, what we end up doing is that we multiply our K values, okay? So I don't have a very good example for this right away, but if we were to add our reactions like when we were doing our Hess's law problems, right? Hess's law, we said, hey, we can add our reactions, we add the enthalpies. In this case, right, we're gonna add the reactions, our equilibrium expression actually is multiplied, okay? So we should be able to multiply those K values together. Now, last little bit here on this page, right? What if we have pure solids or liquids, right? We've talked about our gases, how we use pressures. We've talked about how aqueous solutions, we're going to use the concentrations. But pure solids and pure liquids do not appear in the equilibrium expression, okay? This is really just because we found out that it doesn't really affect the equilibrium in experiments, okay? So this is kind of purely an experimental outcome, okay? So we do not put our solids or liquids in the equilibrium expression, okay? All right, I'm going to pause and come back.